All right. Good morning, everybody. Welcome back. So today, let's continue talking about gases. All right. Let's see where we stopped on Wednesday. Okay. So we actually started talking about transformations. And remember, a gas transformation involves a change in two or more of the characteristics of the gas. We have three main characteristics for the gas: pressure, volume, and temperature. And here, to simplify our study, we are going to consider that all the systems are closed. Okay, so therefore, the number of moles for the gas is always constant. In this case, we can say that the product pressure by volume divided by temperature for the initial state has to be equal to the product pressure times volume over temperature for the final state. Okay, remember, important, the temperature must always be in Kelvin. Okay, the reason for that is to avoid negative temperatures. For pressure and volume, the only thing you must pay attention is that the units at the beginning must be equals to the units at the end. So right now, I want to show you three special transformations. Again, for each transformation, you can always use the PV over T equals to PV over T. The first special gas transformation that I will show you is called Boyle's law. And in this case, the gas transformation occurs at constant temperature. This kind of transformation is also called isothermic. Okay, so if we analyze the word, iso means equal, and thermic comes from temperature. Therefore, gas transformations that occur at constant temperature, they are also called isothermic. The meaning, the initial temperature is going to be equal to the final temperature. Second special gas transformation is described by the Charles law. And in this case, we are going to talk about transformations that occur at constant pressure. This kind of transformation receives a special name of isobaric transformation. And for transformations that occur at constant pressure, the ratio between volume and temperature is going to be constant. Again here, look at the word. Iso means equal. Baric comes from barus, which means pressure. Okay. Therefore, isobaric means the pressure during the transformation is kept constant. Meaning of that, P1, initial pressure, equal to P2, final pressure. Therefore, V over T must be equals to V over T at the end. And the final special transformation, some books call Gay-Lussac law, and those are transformations that occur at constant volume. This kind of transformation may be called isovolumetric, or a fancier name, isochoric. In those kinds of transformations where volume is constant, the ratio between pressure and temperature is constant. Okay? Meaning of that, the initial volume is going to be equal to the final volume. Therefore, P over T initial is equal to P over T final. Okay? Isovolumetric transformations, we are going to keep the volume constant. And look here, always look here at the word isovolumetric. That's very easy. Iso is always equal, and volumetric comes from volume. The fancier name here, same thing. Iso equals, and choric comes from chorus, which means volume. Okay, so a general gas transformation is described by PVT equals to PVT. And within that, we can have three special situations: a transformation at a constant temperature, or constant pressure, or constant volume. In all those cases, you can use the general equation that describes any sort of gas transformation. And then pay attention to which variable is going to be constant, and if something is constant and shows up on both sides of the equation, you may just cancel them. Okay? So start from the general, figure out if there is one of the variables that is kept constant, and then you may cancel this variable and then work with what's left in the equation. All right, let's move on. Okay, so at this point, let's do an exercise to understand how this works. So very simple exercise here. What is the final pressure of 1 mole of ammonia gas, NH3, initially at 1 atmosphere if the temperature of the gas is gradually increased from 0 degrees to 100 degrees Celsius? Assume that the system is closed and the transformation is volumetric. Okay, so I will give you a couple minutes to think about this problem. In the meantime, I'm going to get some water and then we will solve the problem together. Okay, so let me switch to my other screen here, and then we will go over that. All right. So we have a closed system containing ammonia gas, and we are going to increase the temperature of the system from 0 degrees all the way to 100 degrees. And we are going to assume that this transformation is isovolumetric. So first thing that I'm going to do here is try to visualize this system. So for example, here we may have a cylinder, and this cylinder is filled with ammonia gas. Okay. Let's assume that the walls of the cylinder are rigid, therefore they will not change the volume during the transformation. And that's one way to keep the volume always constant. What we are going to do with this system is increase the temperature of the system and move this system to a final state where the temperature now is higher. So let's think about the system first before we start doing any kind of calculations. If there is an increase in the temperature, now the molecules of the gas are going to move faster. The result of this fast movement is now there are more collisions between the gas and the walls of the flask. As a result, the pressure must increase. So before even starting the problem, we have a very strong clue that the pressure must increase. What we are going to do with the equation is just to confirm our initial hypothesis. So always try to visualize the problem, see in which direction, in this case, the pressure is going to move, and then the equation is going to confirm your initial hypothesis, okay? Attention here, we are talking about an isovolumetric transformation. That means the volume is constant. In other words, I can affirm that the initial volume is going to be equals to the final volume. Because this is a gas transformation, I can always write that initial pressure times initial volume over initial temperature equals to final pressure times final volume over final temperature. In this case, the transformation is isovolumetric, which means V1 equals to V2. If we have the same thing showing up on both sides of the equation, you can cancel. You are going to end up with initial pressure over initial temperature equals to final pressure over final temperature. Now, we are going to replace pressure and temperature by the values, and let's see where we will end up. Initial pressure is 1 atmosphere. Initial temperature is 0 degrees Celsius. Therefore, we need to transform that to Kelvin, to 73 Kelvin. So attention to that. We are going to put here 273 Kelvin equals to final pressure. That's what we are looking for, over final temperature, 100 degrees Celsius. Transforming this to Kelvin, we have 373 Kelvin, and we are going to replace right here. Therefore, final pressure, according to my numbers here, is going to be 1.37 atmospheres. Okay, so the unit of pressure is given right here. So therefore, going through the equation just confirmed our initial hypothesis that the pressure increased. Okay, so we started from 1 and went all the way to 1.37 as a result of heating up the sample. And that's how you solve any problems related to gas transformations.
So just to clarify really quick, the value of R given is kind of like making it a trick question in some way because you don't really need to use it.
Yeah, that's correct.
For sure. Thank you.
Yes. Okay, so we have a question here in the chat. So, does the number of mole not change anything in this type of equations? Yes, exactly. Because we are working with a closed system, so that means the number of moles is always constant. Okay, so we are not allowing gas to escape or get in the system. So the number of moles here will not be factored in the equation, as well the gas constant. Okay, so let me see here. All right, we are ready to move on to the next topic. So let's talk really quick about gas density, then we can move on. Okay, so any gas has density, and that will determine if a container filled with gas will float or sink, for example, in the air. So we are going to treat here the gas, any gas, as an ideal gas. For any ideal gas, we can write that PV equals to nRT. I'm going to do an adjustment in this equation. Instead of number of moles, I'm going to replace that by mass over molar mass. Okay, so the number of moles of a gas or any material is always the ratio between the mass that you have over the molar mass. With that, the equation is going to be slightly modified. P times V, mass of the gas over molar mass times R times T. If we are looking for density of anything, we are looking for the ratio between mass and volume. Looking at the ideal gas equation, we have mass on the right side and volume on the left side. So our goal here is going to be to work with the equation to get mass over volume and isolate that from the rest of the equation. So let's do some algebra here in the equation. So what I'm going to do is to move volume to the other side, and that's going to divide. So I'm going to end up with pressure equals to mass over volume. And then I'm going to just do 1 over molar mass. Okay, so molar mass was right here, times R times the temperature. So with that, what we have here now is the ratio between the mass of the gas over temperature, and that's density, okay, right here. So now I will replace mass over volume by density and isolate this term in the equation. Pressure equals to density times 1 over the molar mass times R times T. So now let's isolate the density in this equation. Therefore, density of a gas is always equals to pressure times molar mass over the universal gas constant times the temperature. Okay, and that's how you calculate the density of an ideal gas. If you think about the terms in the equation, it's proportional to the molar mass. So heavier the gas, that will result in a higher density and inversely proportional to the temperature. Remember, if we have a high temperature, we are expanding the gas because the molecules may move faster, and that will result in a decrease of the density.
Excuse me, George.
Yes.
Do you recommend just memorizing that? Because there were a bunch of things in there that didn't really make sense mathematically.
Yes. So what did not make sense mathematically?
It just, there were several steps through there that happened that don't really compute in my brain. It's okay, I can just memorize it.
Yes, yes. Just understand the equation and the factors that change the equation. Okay, so looking at the equation, understand the effect of each term in the density. And that is one of the reasons that moving from sea level to higher altitudes, the percentage of oxygen will decrease. Air is a mixture of nitrogen and oxygen. And as we know, nitrogen is lighter than oxygen. Therefore, when we are at sea level, we have more oxygen because oxygen will tend to move down because again, it's heavier, and going up in the altitude, we will have less oxygen. And here the change can be really fast, moving to not so high altitudes, and a huge effect here on the percentage of oxygen in the air. Okay, so let's move on here and let's talk about the Avogadro's principle and stoichiometry. Okay, so here from now on, things will always circle back to stoichiometry. The Avogadro's principle for ideal gases states that there is a direct relationship between the number of moles and volume of a gas. As we saw before, P times V equals to N times R times T. Therefore, it's clear that there is a direct relationship between number of moles and volume of a gas. And we have a very special condition where 1 mole of any gas, no matter the identity of the gas, occupies the same volume. And this condition is called standard pressure and temperature conditions. Okay, so if we are in the standard pressure and temperature conditions, the pressure and temperature are going to be kept constant and equals to 1 atmosphere and 0 degrees Celsius. Remember that 0 degrees Celsius is the same thing as 273 Kelvin. Therefore, no matter the identity of the gas, if the gas is under the STP conditions, 1 mole of the gas is going to be equals to 22.4 liters. And that's the Avogadro's principle for the ideal gas. 1 mole of any gas will occupy 22.4 liters if the pressure is 1 atmosphere and the temperature is 273 Kelvin. So therefore, we add one more layer of our conversion factor. So we know from the beginning that 1 mole of any substance is equivalent to 6.02 times 10 to the 23rd entities. We can correlate mole with mass using the molar mass. And now, if we are talking about a gas under the standard pressure and temperature conditions, this gas will occupy 22.4 liters. Okay? And that is if the pressure is 1 atmosphere and the temperature 273 Kelvin. And remember, we can use any part of the conversion factor. Okay, so from this point on, we are going to start investigating a little more gases produced in chemical reactions, and we will have to start introducing stoichiometry problems. So let's see how that works in the first example. Calcium carbonate decomposes at high temperatures, producing calcium oxide and carbon dioxide. If 0.25 mole of calcium carbonate is burned, what is the volume of carbon dioxide produced? Assume the standard pressure and temperature conditions and that CO2 behaves as an ideal gas. So first step here is to write the chemical equation. And again, we circle back to nomenclature. Calcium carbonate, CaCO3. That's going to be heat up and produces calcium oxide, CaO, and carbon dioxide, CO2. Okay, CO2 is a gas, calcium oxide is a solid, and calcium carbonate is solid as well. If you want to indicate that there is a heating up process, we draw a triangle over the arrow, okay? So that means we are heating up. So what we have here is basically a chamber where we put the solid, and we are going to collect all the gas produced in a flask right here, okay? Usually above the chamber. So heating up the solid is going to decompose this solid. One of the products is still solid, and the other product that is a gas is going to be collected right here in the chamber, okay? So therefore, we have all the CO2 collected in the chamber above the reaction. We are going to start with 0.25 mole of calcium carbonate. And the goal here is to determine the volume of carbon dioxide produced, assuming that we have the standard pressure and temperature conditions. Because we are talking about the standard pressure and temperature conditions, that means we have a pressure of 1 atmosphere and temperature of 273 Kelvin. Okay, so those are the pressure and temperature conditions that the gas is going to be submitted to. Here, there are two ways to solve the problem. Both ways will need the number of moles of the gas. So that's going to be the first step in solving the problem. So again, we go back to a stoichiometry problem. From the equation, I know that 1 mole of calcium carbonate produces 1 mole of CO2. I'm correlating calcium carbonate with CO2 because calcium carbonate is the only reagent and CO2 is the only gas being produced, and that's where my interest is. So if we start with 0.25 mole of calcium carbonate, how much CO2 is going to be produced? So that's going to be our first very step. So here's a simple proportion problem. 1 mole of calcium carbonate produces 1 mole of CO2. If we have 0.25, how much CO2 is going to be produced? This is basically a proportion. So we can do a cross multiplication, and X is going to be 0.25 mole. Okay. And what I am determining here is the number of moles of CO2 gas. Therefore, we trapped 0.25 moles of gas after the reaction. The question is asking us what is the volume of 0.25 mole of CO2 if we have pressure of 1 atmosphere and temperature of 273 Kelvin. So I'm going to solve that using the ideal gas equation. Let me move here to the other side. Pressure times volume equals to N times R times T. So that's one way to solve the problem. So let me go over that. Pressure is 1, volume is what we are looking for. Number of moles is 0.25. Ideal gas constant, we can go back here and collect the value, which is 0.082, and temperature 273. Solving the equation, we are going to find that the volume of CO2 produced during the after the burning of calcium carbonate is 5.6 liters. Okay, so that's the option number 1 to solve the problem. The option number 2 that we can also solve the problem is using this conversion factor that I just showed you. 1 mole of any gas under the standard pressure and temperature conditions occupies 22.4 liters. So we can then use this conversion factor because we are working under the STP. Okay? So 1 mole of CO2 is equal to 22.4 liters. So this is basically a conversion factor. We have here 1 mole is equivalent to 22.4 liters. The reaction produced 0.25, and this is equivalent to how many liters? Okay. Again, we end up with a very simple proportion. The left side is being divided by 4. Therefore, the right side is going to be divided by 4 as well. Ending here with 5.6 liters. And that's the option number 2 to solve the problem. Okay, so both options, they require you first to determine the number of moles of gas being produced, and then from there you can either use the ideal gas equation or the Avogadro's principle that states that 1 mole of any gas under the standard pressure and temperature conditions occupies a volume of 22.4 liters. Which way I would recommend you to do is the first one, because the first way to solve the problem is the most general one and can be applied to any sort of problems involving generation of gases during a chemical reaction.
Excuse me, Professor.
Yes.
Why did you use the 0.082 in the first method for R?
Okay, so this is a constant, right? So if this is a constant, we can go back to the book and get the value. So I went back here and got 0.082 because for this value, we are working in atmospheres, okay? And the STP is in atmospheres right here. So that is why I got 0.082 and plugged into the equation. Does that answer your question?
It does, yes. Thank you.
Okay, no problem. See, if you have a constant in the equation, you can always go back to the book and plug the value of the constant, okay?
I have a question as well.
Mm-hmm.
So how can you really tell like when you should use the triangle symbol over the arrow for heating up versus like adding oxygen gas, like in a combustion reaction?
Okay, so the triangle is the fanciest and most correct way to represent heating up the reaction. So technically, during the combustion, you are also heating up. So if you want to be 100% correct by the book, in the combustion, you will also add the triangle over the arrow.
Gotcha.
Okay.
Okay.
Every time you have heating up, you add the triangle, and then you are by the book and 100% correct.
Okay.
Okay.
Thank you.
Mm-hmm. Okay, so we don't have time to go over the second example today. So what I'm going to do here is to give you the answer, and then on Monday we will do it together. So the second example is, again, the calcium carbonate decomposition, producing the same products, calcium oxide and carbon dioxide. Now, in this case, I'm giving you the mass of the reagent, okay, attention to that, and telling you that the gas is going to be collected in a 1 liter flask at 25 degrees. And the question asks you about the pressure of the gas. So now all the gas is going to be collected in a 1 liter flask, and the temperature of the gas is going to be kept at 25 degrees. How can we find the pressure of the gas? You are going to basically follow the same flow. The first step is always to find the number of moles of the gas produced, and then you input in the ideal gas equation because we are looking for pressure. And attention here, because now you have a volume of the flask, that's going to be the volume of the gas, and the temperature is going to be slightly different from the first case. So if you solve all of that, you must find a pressure for the gas of 0.50 atmospheres. And with that, I will stop at this point and we will resume on Monday. Okay, hope you have a good weekend and I will see you next week.